Hi, I'm Henry Segerman. This is the Hyperbolic 29 puzzle. This is what you find at the end of the slippery slope of making the classic 15 puzzle more hyperbolic. The first step was this, the 15 plus 4 puzzle, in which a single vertex has 5 squares around it instead of the usual 4. In this, the Hyperbolic 29 puzzle, every vertex has 5 squares around it. This has a lot more squares. The whole thing has 30 of them, up from 16 when everything was flat. With the 15 plus 4 puzzle, it made sense to have the numbered tiles look more or less the same as in the 15 puzzle, but here there's just no way to put things in neat rows. Instead, the numbers go in a spiral from the center outwards. Each tile has an arrow that points to where the next number should be in this solved state. It's hard to see what the bigger pattern is though, so here's the pattern drawn out in the Poincaré disk model of the hyperbolic plane. This is a simulation of the puzzle made by the creators of HyperRogue, which you can play with at this link. I'll also put it in the description. If you haven't heard of HyperRogue, it's an amazing roguelike game set in the hyperbolic plane. Each biome has its own distinct challenges, many of them directly involving the non-Euclidean geometry of the world. In the HyperRogue simulation, it's easy to slide the tiles around. In the physical puzzle, as in the 15 plus 4 puzzle, when two neighboring squares are flat, you can slide a tile across. There is, however, a new problem, a little mini puzzle to solve before making a move. How do I, in fact, get those two neighboring squares flat? The tricky thing here is that you can't bend just one hinge. The hinges extend to make a line going across the whole puzzle, and if there are already squares bent up and down along that line, you just can't make the bend. So you have to get the other stuff out of the way first. I've tested that you can get every single hinge in this puzzle flat, although I don't fully understand the configuration space here. To illustrate some of the complexity, here's a smaller version of the puzzle, the Hyperbolic 12 puzzle, which has only 13 squares. Here I've put it together in a bad configuration. There's no way to make any bends at all because of the way the four corner parts alternate pointing up and down. If, however, I switch one of the up corners to down, then there's a sequence of bends that gets me to the all down corner state, and from here you can make any of the edges flat. I suspect, but I haven't proved, that the configuration space of this version of the puzzle has the two isolated configurations when the corner parts alternate up and down, and then everything else is in one big component. Here in the full puzzle again, it's more complicated. There are surely many bad ways to bolt this together in space that would not allow you to bend every hinge flat. So here's a challenge. What is the configuration space of the frame? How many connected components does it have, and which components allow you to fold every hinge flat? The 15 puzzle famously has inaccessible permutations of its tiles due to a parity argument that depends on the fact that there are 4 squares around each vertex. This isn't true for the 15 plus 4 puzzle, and it turns out that this means that every permutation is accessible. However, the orientation of the tiles now matters because moving a tile around the central vertex rotates it by 90 degrees. If you also care about the orientation of the tiles, then you again cannot get to every configuration. I don't think anyone has formally written up a proof of this yet, but Zach Abel checked computationally that there is exactly one parity condition. So what about the Hyperbolic 29 puzzle? Assuming that you can always slide a tile across between any two neighboring squares, can you get to all permutations and rotations of the tiles? Or, as in the other puzzles, are there some restrictions? Another natural question to ask is, what happens if we try to make it bigger? So this puzzle is what you get by starting with a single vertex, adding the 5 squares next to that vertex, and then adding all the squares that touch those 5. Can we add another layer of squares onto the outside? Or can we add another layer of squares onto the outside of the Hyperbolic 12 puzzle? This would get us to 61 or 125 squares respectively. It might be possible to add them on without collisions, but even if you could, I very much doubt that the bending configuration space would work out so that you'd be able to slide the tiles across every hinge. In the HyperRogue simulation, of course, this is no problem. The construction of this puzzle is very similar to what I did for the 15 plus 4 puzzle. I'm using the same nuts and bolts for the hinges. The tiles are a little bit different, with 4 feet at the corners rather than one big foot in the middle. This is a little bit less sturdy, but it's necessary to dodge the single bolt hinge between two neighboring tiles. This time I switched to a neater way of doing the numbers, which was suggested by my brother Will. Instead of painting them on, these are 3D printed on a desktop printer and then glued on to the Shapeways printed tiles. I've put a link for the files to print your own numbers in the description. Alright, this is the Hyperbolic 29 puzzle. Thanks for watching.